Hello guys, welcome back to CFD College. I'm Ashkan and this is the third part of tutorial on flow over a cylinder. The simulation of this flow in ANSYS Fluent. In the first part, we created the 2D domain and the structured mesh. In the second part, we simulated the flow in Reynolds number of 20. And this is the third part. In this video, we are going to simulate the process, the airflow passing a cylinder in high Reynolds number 200. If you remember, in when Reynolds is 200, we have still laminar flow, both for wedge and the boundary layer. But in this situation, we have Vortex Street, we have Von-Karman Vortex Street. So the simulation cannot be done in steady state. We should use transient, and this is a good example for you to understand, to learn how you can perform transient simulation. So before starting this video officially, please subscribe the channel if you haven't done that. Please share the videos with your friends and give us a thumbs up. That's the only support I needed from you. Okay, so Reynolds number is 200. Let's go to the Excel file. Now Reynolds number is 200 and it's easy as you know. We just need to multiply the velocity by 10 in order to get this Reynolds number. So now velocity should be 2.94 times 10 to minus 3. Let's jump to the workbench. You just need to duplicate the first block. You don't need to generate the mesh or the domain from the scratch. When you are working with workbench, there is this capability. You can just duplicate your project, your blocks, and as you can see, all the settings up to the calculation point, So you have the geometry, you have the mesh, and you have the settings for the setup for the solver all available here. There is no need to do all those steps again. So just let me rename this. This is steady flow and Reynolds number is 220. Always keep in mind that it's better to rename the blocks because after a while you will forget what these blocks are. This is transient flow. Reynolds number equals 200. So I open setup, and here in this simulation, I will use 4 processors because it's transient. Transient simulations are usually costly in both ways. System, in terms of system, you need more powerful CPU and more RAM. And of course, it's time consuming because in steady state simulation, there is no time step iterations. So here we have time steps, and in each time steps we have 50, 60, 100 iterations. And mostly we have to reduce the time step size to get a good convergence. So transient simulations are usually timely. Okay, all the settings are the same, but time. Here we need to choose transient. So in this ANSYS is 2022 R1. Uh, I think in 2020 and later, the version of ANSYS I mean, uh, there is no issue when you change the time from steady to transient with regard to report definitions. It automatically switches from iterations to time step. It's not a big deal. Okay, so the flow is still laminar. We are in laminar region. There is no need to activate the energy equation because for now uh, we don't need to solve energy equation. Uh, the flow is laminar and the fluid is air. If you check, you can see viscosity is 1.8 10 to minus 5. Right, it's the same value as I modified in the previous tutorial. Yeah. Uh, this is subzone condition. No need to change that. Boundary conditions. We need to modify inlet velocity. Okay, so I remove one of these zeros. And the other boundary conditions are the same as you can see. Reference values, do that again because here velocity is higher. Method is simple because it's transient, and simple scheme is a bit faster than coupled. It's because of its calculations. And let me, okay, in transient simulation, it's wise. I suggest you to uh, choose an appropriate value for these residuals. I think for this problem, 10 to minus 6 or 10 to minus 5 is appropriate, is suitable. And let's initialize the flow. Okay, now we have new parameters: number of time step size, maximum iteration per time step. For time step size, time step size depends on the project, on the physics, on the phenomena. For example, uh, in this example, the velocity of the flow is let's say 3 millimeters per second. This distance is, I think, about 15 meters. Some, mm, I don't know. It's about 1 times 5 meters. Sorry. So 3 millimeters per second. So I think uh, time step size can be near 25 seconds. So in each time step, the flow moved for how much? 75 millimeters, and I think it's good. So the number of time steps, I don't know, depends on you. For example, 100, I think 200 should be enough for me. So it means that I want to simulate this phenomena for 5,000 seconds, if I'm not mistaken. Yeah. And the maximum iterations per time step, 20 is in most cases, 20 is not sufficient. Usually you need to increase it in order to make sure of convergence at all the time steps. Okay, so let's decrease the number of time steps to 100. Then after that, we can think about it, whether we need to continue or not. In transient simulations, it's good to, let me delete this and this. It's good to uh, save data file every, for example, 1 second, or every, for example, 5 time steps. You should do that because in transient simulations, after the simulation is finished, you need to see or report different contours, velocity vectors, streamlines, I don't know, different charts at different instances. So to do that, you need to have the data. First method is to save the data file. The second method is to save uh, some quantities using solution data export, which is an automatic export. In the first one, the size of the file would be large because in data file, many quantities are included. So the size of the file is much bigger than the automatic export. For example, uh, you have two options. You can say, I want the data file every 10 seconds, 50 seconds, or every time 5 time steps, or like that. Um, for me, I think I want to save the data file every 10 time steps. It should be good. And the file name, it's better to append with time step in this way. And when you want to make an animation from a transient simulation, you need many frames. Using 10 frames, you can make a good animation. So, but if you want to save, for example, 1,000 or 500 frames, you need a huge space on your disk because the data file is so big. That's why we use automatic export. Click on Create and Solution Data Export. If you do that, you can change the file type to CFD-Post. You can see here on the right, you can select the quantity that you want. For example, here, if I want to make animation, I would choose static pressure, velocity magnitude, and let's say vorticity magnitude. Not all these quantities. You don't need to make animation of all of these. So since the number of quantities is much less, you pick only few quantities, you can decrease the export data frequency, for example, to 1 time step. And you can deselect this one if the mesh file is fixed, or let's say if you don't have, for example, dynamic mesh. And then you can use these files in Insight or CFD-Post. You can use, if you want to use TechPlot to make the animation, TechPlot can work with case and data Fluent case and data files. So you can you can make the animation using data files of the Fluent. But if you are working with standalone CFD-Post, I mean, if you are not working in Workbench, then in new versions of ANSYS, I think 2021 or 2022 and newer versions, uh, you cannot import uh, data, case and data file of the transient simulation in standalone CFD-Post. If you are working in Workbench, you can use CFD-Post without the need of saving automatic export if you don't have any limit on your space, disk space. But if you want to work with the standalone CFD-Post like this, you should create it of this automatic export. I think I have a video uh, about making animation in CFD-Post. It's better for you to watch that video because there are lots of details in that video. And there is another way, which is making the animation using ANSYS Fluent. I will teach you in another tutorial how to make animation in ANSYS Fluent using ANSYS Fluent, but not in this tutorial because we usually don't use that. The output file from Fluent, the animation, I mean, it's not good to reporting. I don't know the defense or meetings. So now I think we are ready. We can click on calculate and wait for the simulation to finish. You can check the drag coefficient. You should see if you have a vortex shedding, if you have a Von-Karman Vortex Street, drag coefficient should fluctuate, and you have to see that in this plot. Meanwhile, you should check residuals. As you can see, the convergency of this project is good. At every time step, the flow is converged in, I think, 44 iterations. Let's look at CD. Anytime you can stop the simulation. I think you can see that here using stop at the end of time step. When you are when you have a transient simulation, never click on stop at the end of the iteration. You should always use this one, stop at the end of time step. But maybe you don't need the calculation. For example, you find out something is wrong, then you can click on the first button. But if you want to examine the results, the flow field in the middle of a simulation, you should click on stop at the end of time step. For example, let me click on that. Let us check the contours, the velocity contour. Oh, here you can see something is happening. So we have to continue the calculations. Sometimes, because of this sudden peak of any parameter, CD, CL, and any parameter, you won't be able to see the fluctuations because of the range. You can modify the range, but you can also check the contour as I did a few seconds ago. In transient simulation, always check the convergency. Let me check the velocity field again. It's better. In order to increase the accuracy, you may change the transient formulation from first order to second order. In these kinds of problems, it will help the accuracy of the solution. I know it's more, uh, it has more computational cost, but the accuracy is higher also. Let me check the velocity field again. So we are close to see the vortex shedding. Okay, I think we should let the simulation run. So I pause the video. Let me fix this. So let me pause the video, and when the calculation is finished, we will come back and post and see the results. Uh, Hello again. Let's check the velocity field. It's better. I think we can increase the time step size. So it's the number of time step is 187. So I need 13 more time steps. Yes, it's now 8. I want to reach the 200 time step. Okay, now let's check the velocity field and let's increase the time step size to 100. Meanwhile, let me show you uh, here. You can see the workbench folder in dpserv fff1 fluent. You can see the stored files. These are the fluent data files. .dat.h5, and these cdat files are generated from our automatic export. So we can import these files into a standalone CFD-Post. Let's see what happened. We should have decreased the size of the cylinder, and that would solve the problem, I think, because now we need to wait too much. Okay, now I think it's enough. As you can see here, we can see the fluctuations in drag coefficient. Uh, so let me stop the simulation, check the velocity contour. Yeah, you can see vortex. And now you can realize why I mentioned, we need a bigger domain in such these simulations. So if you are working on your thesis, please use bigger domains. This is only is only an educational example, but in your projects, you should use a bigger domain. So let me close. Let me check it. We can. Uh, yeah. I think it's better to let simulation goes a bit further. Okay, now let me close Fluent and open CFD-Post. But before that, when you see this sign, right click and on the solution and click on accept interrupted solution as up to date, then open CFD-Post. Oh, okay. So it can't be open because I think uh, file is corrupted, so it doesn't matter. I can use standalone CFD-Post. This is the benefit when you have saved CDAT files for CFD-Post. So you just need to click on the last CDAT file and then click on open, wait for the software, and it's done. Right click, predefined camera. This is good. Then you can, if you have seen my videos on CFD-Post, now you know what I'm doing and you don't have any problems. So symmetry 1, I want to see velocity contour. As you can see, it's this one. Let me modify the legend. Again, be sure that you have watched all my videos on CFD-Post. I explained all these settings. Then click on animation button and you can click on play to see the animation, to see the Von-Karman Street. See, this is how flow evaluate. This is the flow evolution. And I think we should see Von-Karman Street in seconds. Now I have too many frames, as you can see. But if I think now it's good because the animation, you can see the animation uh, has high quality because of the number of frames. Let me pause the animation and now it's better. Now we can see the velocities. Let me check the vorticity contour on symmetry 2. Vorticity. For vorticity, we have to reduce the maximum value. For example, or even smaller value. Now let's see vorticity contour. This is vorticity magnitude. If you pick Z vorticity, then you will see different colors for these vortices. For example, the upper vortices are red and the lower vortices will be blue, I think. See, this is how you can simulate transient simulation. This is a benchmark project in ANSYS Fluent. And I think it's good to start with these benchmark, especially if you are a beginner. So now in this video, you understand how to simulate a transient simulation and, the time step, the saving of the data files, the autosave and everything else. I hope you enjoyed it and I hope you can use it. But just for the last point, if you want to save this animation, you just need to check this save movie option. Specify the location, yes, and the format, MPEG-4 or AVI, and in the option you can control the frame rate. So the frame rate 24 is okay, but you need to have many frames. Don't forget that. So I think that's it for this tutorial. I hope you've enjoyed it. If it's the case, please give us a thumbs up, share this video with your friends, and subscribe this channel. I have lots of videos about CFD and numerical simulations. So thank you for watching this video. Until the next video, take care of yourselves and bye bye.